Lecture 2, Section 2 and Part 2. In the first part of this section, we had the two terms for the objective function. The first one was the expected holding cost, and the second one was the expected ordering or setup cost. And here we're going to have the third term, which is expected penalty cost. So during the lead time, we may have shortage, right? So let's say at the time that we place a new order, we have our units in our inventory. So, and let's show the demand during the lead time by D. That's a random variable, right? So this D could be less than or equal to R, or it could be greater than R, right? But in cases that D is less than or equal to R, so there is no shortage, right? But if demand becomes greater than R, then in that case we have shortage, right? So in order to calculate the expected number of units short, we need to write this expression. So expected value of maximum between D minus R and 0. So here we need to consider the values for demand during the lead time which are greater than R. So as you see here, we consider X as demand during the lead time, and we consider just the number values for X be greater than or equal to R up to infinity, and then we need to multiply this term by the PDF, and then by taking the sum over the values, which will be the integral here, then we obtain the expected number of shorts units short. Okay. And so here, let's show this expected number of shortage by NR. So NR is the expected number of units short during the lead time. Okay, so or we can say unsatisfied demand, or yeah, expected number of units short. Okay, and so that's for one cycle. I mean, during one period of the lead time. But as you know, we have multiple cycles in our time unit, let's say in a year. So in order to have this expected number of shorts during the time unit, so we need to multiply this by the number of cycles per year or per time unit. And as you know, 1 over T is the number of cycles, so NR times 1 over T, or lambda over Q is the number of cycles, so lambda over Q times NR. Okay, and now we have the expected number of shortages per year time unit, and if we multiply this by P, the unit cost of, the unit penalty cost of the shortage, then we will have the expected penalty cost per time unit or per year. Okay. The last term here is the expected purchase cost per time unit or per year. And since here we have mean of land, the mean demand of lambda per year, so we are expected to buy lambda units of the good, right? And if we multiply this by C, it will be the expected purchase cost per year. But same as the EOQ model, this term has no impact in our optimization, so we can ignore this term in our objective function because it has no influence, because we are going to take the first derivative of the cost function in terms of Q and R, and there is no Q or R in this term, so this term will have no impact on optimization. Okay. But this doesn't mean that we are going to eliminate the C, the unit purchase price, because in H we do have C, because H equals I times C. So yeah, the unit purchase price has impact on our optimization, but not the total or the expected total purchase price. Okay, purchase cost. Okay. So now we can write the objective function, the average annual cost or expected annual cost. Here we have three terms. The first term is the expected or average holding cost per year. The second term is the expected ordering or setup cost, and the third term here is the expected penalty cost. Okay, and so now we have this objective function, and we do have two decision variables, which are q and r, right? So if we take the first derivative of this function with respect to q and r, and then set them to be 0, and then by solving those two equations, we can obtain these two equations for calculating q and r. Okay, so as you see here, we have two equations, and we need to solve these two equations simultaneously in order to obtain the value of q and r. Okay, so as you see here in q, we have a term. Let me show with a different color here, like this. So we have the nr here, and here we have also r. So yeah, I mean, we need to start from an initial value for q. Then by having that initial value for q, we can obtain r, and then by having this r, we can obtain nr, and then by having that nr, we can obtain a new q here. And then we said we will replace this new q here again in order to obtain a new value for r. And so we continue this process until we converge to a value for q and r, and in that time we stop there, and then the last value for q and r will be the optimal value. Okay, so the solution procedure, as I said, we need to start from a starting point, an initial value for q, which we can set it as EOQ, right? Yeah, we can actually ignore the uncertainty, and then by assuming that demand is constant by lambda, so we can obtain the EOQ value here. We can consider this as the initial value for q and show this by q0, and then by having q0 we obtain r0, and then by having r0 we can obtain nr, and then by having this nr we can obtain a new value for q, which we call here it as q1, and then by q1 we obtain r1, and so we continue this process until convergence. So I mean, until the values of q and r converge to a value that they don't change by continuing the process. So, and those numbers, those values will be the optimal values of q and r. Okay, so in the solution procedure, by having an r, we need to obtain nr. So let's see how can we do this. We obtain nr by using the standardized loss function. Okay, so nr equals sigma times LZ. Sigma actually here is the standard deviation, and LZ is called standardized loss function. And the Z is this R minus mu divided by sigma. And as you remember in your statistics course, if you have a normal distribution, you can convert that to a standard normal distribution by subtracting that value mu from that value and then divide that by sigma, right? So yeah, here we call the Z as safety factor here, and that's the standard value for our normal distribution. Then by having the Z, you can go to a table in A4, table A4 at the end of the textbook, but I will upload this table in Learn, so you will have this table, and then by having a Z, you can go to that table and obtain the LZ value. So by having that LZ value, you can multiply that by sigma, and then by doing that, you're obtaining the value for NR. Okay. So here we have an example 5.4 from the textbook, page 270. I will solve this example in our live session on Tuesday, but you may try by your own to see if you can solve this question by following that iteration procedure, solution procedure that we have learned so far. So yeah, if you can, please try that. But I will solve this example live in our live lecture session on Tuesday. Okay. So yeah, we'll obtain these quantities in the live session. Let's assume that we have solved that example, and now we want to obtain the proportion of order cycles in which no stock outs occur. So yeah, we have cycles with the length of t, and we want to see what's the proportion that there is no stock out situation. Okay, so this means that we need to have this, right? The probability of demand during the lead time be less than or equal to r. Okay, so if you remember, we had this equation. The second equation was this: 1 minus fr equals q times h divided by p times lambda, right? So by having this, we can obtain the fr like this. Okay, so this will be the probability that we won't have a stock out situation during the lead time, and then if you multiply this ratio by 100%, that will be the percentage of having no stock out during the ordering cycle. Okay. Or we can obtain the proportion of demands that are not met. So in any cycle, we assume that the expected demand is Q, right? Our order size. And that's exactly equal to the expected demand during that cycle. And again, in any cycle, the expected number of shortage is NR, right? So now if we divide NR by Q, that will be the proportion of demand that is not satisfied, right? And yeah, and that's it. Or we can say 1 minus NR divided by Q times 100, then this will be the percentage of demand that are satisfied, right? Yeah, that's for, this is called somehow the service level. We will have this later in our course, but this means that let's say it's 99%, for example. This means that with 99%, we are satisfying demand during the lead time, or we can say 99% of demands in average during the lead time are satisfied, and just 1%, again in average expected, is unsatisfied demand during the cycle. Okay. So far in the models that we had so far, we consider the inventory level, right? As you remember, but if at this point we have a new order, we are placing a new order at this time, we can actually define another term here, which is inventory position. Okay, so at this time, when we place a new order, the inventory position increases to R plus Q, right? And by declining the inventory level, this inventory position declines as well. And so as you see here, we have the inventory position. So this is actually the sum of total stock on hand plus inventory on order, or it's also called inventory on the way. So they are on the way coming to our warehouse, right? So in general, we can say that we need to know if we have inventory on the order and it's supposed to be in our stock soon. So we need to consider this instead of inventory level for our decisions, right? So in the next section, you will see how we consider the inventory position in making our decisions. Okay, so this is the end of part 2 of section 2. So and that's it. This is the content for week 4. And in the next section, next week in the next section of chapter 5, we will have more models in written model with uncertain demands. Okay, thank you.